Hello everybody and welcome to the second Smart Homes Ecosystem webinar from the University of Salford. My name's Nigel Blanford. I'm part of the Energy House 2 team, and this has been brought to you by the European Regional Development Fund, specifically with some funding from them. So this Smart Homes webinar series, it does have a bias on energy, but let's just say that the concept and skills will extend beyond that, beyond the home of the whole of the smart homes arena. But obviously, one of the reasons we do concentrate on the energy side, not only because that's our skill, obviously, as you can see, Energy House, but also because that's where you can save money. So we are here principally as part of the Energy House 2 programme at this stage to assist Greater Manchester small and medium-sized enterprises. Those of you from outside Greater Manchester have them to thank for these sessions. Having attended these webinars, these Greater Manchester SMEs will be in the position to potentially access our services at zero cost. Other companies are welcome to have their products tested by us, but this will be on a commercial basis. Just noting that all of you have been placed on mute at the moment. There will be time for questions and answers after the end of each session. These are carried out via a text facility, so up there you'll see a little question mark box. You can type your questions into there. They come through to us and then we can forward them on to the speakers or myself or Yanis, who is also on the the answering panel here. We've allowed generous time for questions and answers after each session, but if these aren't full, if this time slot after the session isn't fully used up, we will just advance the programme forward, which will result the session finishing before the due time. There is a comfort break for about 15 minutes halfway through the session, so between Josh and Carolus, and we've set up severally individual named meeting rooms. These will pop up at the break. You'll see the URLs there, and I've also emailed you. So one of the bit of feedback from yesterday was, can you just email the links so we don't have to type it in? That's been done. And I won't be calling you back in after the session either, after the comfort break either. So you'll have to make sure you come back in again. Please be patient. This is, like I was saying yesterday, this is our first attempt at a webinar, so there might be a few hiccups. By the end of this series, hopefully we'd have got to grips with it. So this is new to us. Another thing is I don't need to tell you about the fire procedures, the toilets, or to put your phones on mute. Although I will ask all those in the presenting room if they aren't on mute to mute their phones. Throughout these 4 sessions, there will be something that you can gain. They are pitched so that while some subjects may fall outside your full technical understanding, you will understand the concepts which can be applied to your specific area of knowledge. So without further ado, I'd like to introduce Josh Cooper from Hildebrand. A little bio here. Joshua acquired Hildebrand with Clive in 2004. He's been working with startups in the technical leadership role for nearly 20 years. He's currently CEO of Hildebrand, board member of Freerunner, an indoor positioning and retail analytics company. He has founded 2 technology companies that reached the Times Tech Track 100, including Bolt Blue, that created the global ringtone market and boasted 15 million subscribers, as well as CTO of Spinvox, raising over $200 million in investment and awarded the prestigious GSM Association Mobile Innovation Award. His research and development leadership has been in directing DHEMS, a £4 million FP7 and R&D project, Shoreditch Digital Bridge, and currently working on 2 FP7 Smart Cities projects, EPIC and Cosmos. Joshua holds a BSc in Biomedical Engineering from Rensselaer in New York, USA. I think I've said Rensselaer right there. But yes, without further ado, Josh, over to you.
Thanks, Nigel. Yeah, this is my first time using the Teams Live stuff as well, so hopefully go without a hitch. but somebody shout and wave your hands if it doesn't. Thanks very much for the introduction. Today I'm going to be sort of guiding you through some hands-on exercises, as well as demonstrating some of the things that we're working on in the smart metering and specifically in smart tariff areas. You should probably have gotten a slide pack from us where we have a couple of sort of prerequisites, I suppose. These are not absolutely necessary that you have logged into these. I'll be going through them, but they're there for your reference. The first being, if you want access to your smart meter data, if you have a smart meter, please feel free to follow along and do this with us. The next is around using that data in a notebook environment called Observable HQ. If you've had a little chance to go through that, you know, that's also a good thing to be able to do. And again, if you're not familiar with coding, it's not really something you need to understand too much about the coding principles, but more to just give it a try. I think you should get some results without necessarily knowing too much about coding today. Okay, with that, what we're going to do is switch over to a hopefully web view of Smart Tariff, smartcomparison.org. There's some background material in the slide deck, and I'm not going to go through that in you know, slide by slide detail. Smart Tariff is a project sponsored by Bayes. They came to us with a requirement of figuring out how to, I guess, view smart tariffs with smart meter data in a kind of new smart meter world where, you know, your actual price could be calculated on a half-hourly basis for complex tariffs like Agile, if you're familiar with that, or time of use tariffs. Some of the background material about those tariff structures are in the slide deck, but basically with the grid, we have issues around capacity. So we have peak times, usually in the evenings, where electricity is in short supply or quite expensive. Oops. Is that, Giannis, is that saying something to me? Oh, sorry, okay. And when we have short supply of electricity, the price usually goes up with that. Same could be with renewables. So if you have wind or solar, they have large impacts on the wholesale price of energy. And those pricing signals are helpful in terms of the overall grid management and optimization. You know, if the market's working properly, then, you know, higher prices should mean less demand. So there's internationally or, you know, globally a big push to have tariffs be you know, responsive and send price signals, and smart meters enable that. So the Smart Tariff Smart Comparison website has two sections. One, we're going to start with the kind of just show you some of the registration elements, just to make sure that if you'd like to get signed up, how you can do that. This is going to use live data from your smart meter if you were to type it in. So the first thing we're looking at is getting the security information from you. I'm going to say no to knowing more about smart meters, and go through and enter a postcode. So the postcode is the postcode of the smart meter that is in your house. I've got a sort of an example I'm just going to run through really quickly. So I'm going to type the postcode of the office in here. And then the next thing we would do is we'll look up a EUI or GUID that's on the back of your in-home display. If you have a smart meter, you were probably given an in-home display. And I'll just actually hold one of those up for you here on camera. And hopefully that will be able to be seen in the small box. So there's a code printed, a long code, either EUID or GUID, and that will enable you to kind of clear. We looked this up in a database, and that means you can kind of clear security, and we know that it's you. If you're doing this as we go along, you know, type it in. It's a little fiddly. It's 16 characters, and you should sort of get to the end of this. I'm gonna skip typing that in because it's not particularly entertaining to see that. Let's just see. Okay, so there's already an account that we've got. So once we've registered you, we then go off and we get data from the smart meter infrastructure, and we're connecting to that meter. It's going to load then a set of data. It does take a couple of minutes because we load a tariff for the whole year, and so this is half hour by half hour calculated. And it will give us a current cost. Hopefully this can be sort of seen in the orange color, versus a tariff that has been put up as a kind of comparison. The graph's interactive, so being able to click on these various tariffs, you can see we're actually on this. This is the Agile Tariff, if you're familiar with that. We've renamed it Dynamo Pair just to be a little bit friendlier to Octopus Energy. You can see that it's mirroring that. You know, that's our actual tariff. And I can go in then and begin to filter based on whether I'm interested in maybe a time of use tariff. So this is one of their EV tariffs that varies time, and I can see if I clicked on that, my spend would have actually increased. I'm on a very good tariff, obviously, if I'm on Agile at the moment. And then we can do some things like look at average daily profile. So this is my actual half-hour usage average for Monday, Tuesday, Wednesday across the entire year. So I've got this kind of noticeable pattern, like most people do, of evening use. And with COVID, there's probably a bit more use during the day as well. We're interested then to sort of see if we shift that pattern. So if I was to say shift my peak load, and here the rules can be seen in here. So between 6:30 and 8:30, if we shift that to midnight to 2 a.m., if I want to shift, say, 10% of my load, you can kind of see that these areas are increasing. And we're working on data across the entire year. So there's 19,200 data points being manipulated through this kind of reallocation of peak times to non-peak times. And we can flip back to the monthly graph, and we can start to see how that might change my spend. Now, this is going to be more profound for people who don't have Agile Tariff. By shifting and adding electric vehicle, you should start to see some differences in spend. And I can kind of erase those parameters as well. Going back to average daily we're going to look at the add electric vehicle. And what we're simulating there is if I was to purchase an electric vehicle, then that's going to mean overnight I'd like to charge that vehicle up. If I'm a commuter, that makes a big difference in the overnight load. You can sort of see the before and after by clicking on that. And that will impact cost enormously. So hopefully this is sort of visible, but the red that's been added shows the additional cost of having an electric vehicle. Okay, so then you can begin to, again, start to look at these tariffs and how they will be recommended. Are they going to be suitable for the type of use that I might have? So if I go back to my Agile Tariff, I'm saving considerable amount of money every year if I had an electric vehicle, if I was on the dynamo pair from if I was on some other tariff. And I can then click and view all results and sort of sort based on various annual cost calculations. Now this is using my historical data, so it's not necessarily a reflection of what the future might hold, but it's a very good approximation of that if my behavior pretty much stays the same year on year. What we're hoping to do with this project is to illustrate that by adding a selection of tariffs, using real consumption information, which we're doing, and then combining that with low carbon technologies, people should be able to understand better what their affordability of, say, a heat pump or an electric vehicle, or what's the additional cost benefit of say, solar panels on my household. So we're going to be developing a number. These are some basic ones. So the shifting is like a battery, an electric vehicle, of course, is what it is. But we're probably going to have more configurable parameters on this, so you can say what size of electric vehicle you want it to add, what size of battery that might work for shifting, and then also doing some optimization to tell you what technologies might actually work best for your situation. So all that being kind of a product that somebody could come in and use, we would really like to see price comparison websites and/or energy companies, to kind of take up this sort of technology and embed it. So you can imagine if you're a supplier, you might want to just show your tariffs. You might not want to be comparing everything under the sun and switching people away from you unless your prices are so much better than everyone else's. But what we're kind of thinking is that if you could, between say an EV tariff, an Agile tariff, or a standard flat rate tariff, begin to get your customers to understand what's a good fit for them, that we think that will increase the take up of smart tariffs. It'll illustrate the kind of benefit of having a smart meter and what dynamic pricing could do for people. So when they're doing that, we are providing them with a library. And that library is written in JavaScript. All the examples I just showed you are executing on the browser locally so that it's not kind of going out to a server and calculating and coming back. The source data is coming from a server. So if you're technically minded, this makes sense. If you're not, it may have to think of it a little bit like a database of tariffs, a database of your energy data, but the computation that's coming back from those servers is happening here locally on the browser that I'm running in. And that means that the code library that runs on the browser could be used by anyone to perform these calculations and to experiment with these calculations, to analyze energy data in general, or tariffs in general, or the combination of the two, which is the cost of a potential energy tariff. So what I'm going to do at the minute is to switch over to observable. If you hopefully could see this, URL that I'm highlighting. I don't know if I can make it bigger in any way. Let's see if we go in here, let's cut and paste it in here. And hopefully some of you will have been able to manage to get through this a little bit. So it's just at Joshua Cooper, so you can search on observablehq.com. You should be able to find that, or type that in directly. And then if you navigate to at Joshua Cooper, the notebooks should be available there. I'll give you just a minute to catch up with that while I take a sip of water. Okay, so there are 3 notebooks. The first one is just about how to load your energy data. And let's see if we can zoom in just a little bit on that. Hopefully, it's hopefully there. So we have a couple of kind of background bits that you can feel free to click on at your own time. We don't need to go through this today, but this is where the source code of this library is published. And we're publishing it as open source code, and it'll be maintained for another 3 to 4 months before we're finished with the project. So we'll be adding more features. If you're familiar with code repositories, you can check that code out yourself and manipulate it and do your own programming around it. If you're not, this environment with this notebook is really really quite good. If you've not used these notebooks before, on the left there are these ellipses that expand and contract, so you can potentially see the results here where this is text, and when I expand this, you can see the code that sits behind that, which is some markup language. Also, notice down at the bottom, if I scroll all the way down at the bottom, we're including, we're importing some things, and they're being then used higher up in the notebook. So the idea is the notebook's not linear, so it doesn't execute code down the page. It's all sort of executing at once, let's say. So what I've done is I put some of the kind of trickier library stuff down at the bottom to get it out of the way. We're going to go through it though, and then try to get some of the nice graphical bits sort of at the top. So when we sort of look at what these examples are trying to show is we're trying to show that we can access data at a half-hourly granularity. That then we've got some function calls that we can make to summarize that data so that it's more useful. 19,200 data points. For a whole year's worth of data is very hard to interpret as a big, long chunk of data. So summarizing it into weekly, daily, hourly, and calculating statistics on it is quite important. And we're doing some of that sort of heavy lifting. And then we're going to be looking at some of the kind of summaries that represent what we call behavioral features, and talk through a little bit of why those are interesting. So to start with, we've got the library which I talked about. We're including that, so this stsc-tsc at, and this is just the version number that I'm working off of. It's a version that I know will work. We've got some more recent versions, but this version is one that's been tested for this. This basically loads all the code that we've written, and you can furthermore sort of see what that is exposing. So it's exposing what are called in programming terms classes. So these are objects which in code represent concepts. So we've got the main STSC class, which is just sort of an artificial concept. So it's our smart tariff, smart comparison, kind of all-encompassing class. We have a time series. So this is a general thing where time series is basically values keyed by timestamps. So if you think of the fundamental energy data, it's a time series. We're capturing, every half hour a reading or a value of consumption, and we'll be manipulating data in a time series. Energy is a special type of time series, so it actually inherits some of its properties of the general time series, but energy is special in that we know that it's half-hourly buckets, so we expect to see a certain number of readings per day, etc. And it's got special properties like if we take an average or a minimal or maximal of energy, we don't expect it to be negative. We expect 0 to be kind of like the lowest value that you can consume in terms of energy. And then there are some kind of practical upper boundaries. So we never see any sort of negative numbers. And also the way we record energy from a meter isn't fractional. So it's always in whole units of watt hours. So there's some assumptions that are made. Tariffs, again, is also can be a time series. It's in the case where we have dynamic tariffs, it's going to be something that has a price every half hour that's constantly changing. These are quite interesting things. And the Agile Tariff that some of you may be familiar with changes every day, basically. So 2 days ahead, you can see the price that you'll be paying. So today we can see the price that we'd be paying for Saturday, for instance. So it doesn't necessarily give you a lot of visibility into the future. And there's downsides with having these dynamic tariffs, in that the price can spike and the price can go way up. So if you really need the energy, you don't have control over when you're using the energy. Sometimes these dynamic tariffs are not very good because you could end up being paying a lot when the wholesale price goes up, and you're exposed to that risk. Products are basically how energy tariffs are marketed. So if you think of a product being the word Agile, or the word Go, or British Gas has some tariffs that include things like boiler cover. So those are bundled as products. We're trying to show the kind of, the relative benefits of products versus tariffs. Suppliers, so these are energy suppliers. Cost is then a function of combining a tariff with your energy or some energy, and we can calculate cost either annually, so we can look at the entire cost of these things, or we can look at it half hour by half hour, week by week, day by day, etc. So these are the kind of basic building blocks that we've got in terms of our program that we're looking at, our calculations that we're looking at. So I'm going to close that one down, and I have instanced another one. So this is the code that I've written, and hopefully you should be able to sort of see this. So we have this STSC object, which is called, or this sort of high-level object called my. That's referred to in this area here, and I'm going to create a new energy object now. So the reason why it's a new energy object is I want to populate it with my data. So it's no longer just a hollow shell of a concept called energy. I want to fill it in. I want my data to be filled in. And you should be able to do this, again, without having registered on the website that I showed before. We've got a test token, but if you did have your own token, you would be able to find that. And we're going to make this a little easier to do. But if you do inspect on, go into application, this is your token. So it's this big long security thing that you could select and copy, and you could just paste that right into there. So the energy token will look something like that. Now, for simplicity's sake, I think I won't necessarily work with that one. You can just go ahead and safely use, but if you want to use your actual data, you can cut and paste your token into that. And then what we're doing is we're saying, okay, we're going to load that data associated with this token into my energy and return that. And above is what actually gets returned. So we could even start a new notebook if you wanted to, if you wanted to follow, sort of see how this works in practice. I'm going to just start a new one, and we can just say new notebook, and then I can run that by pressing this run button here. I've got a new notebook, and then I can add a cell underneath that, and it's good to sort of build things up. And then I'm going to go and I'm going to cut and paste. Firstly, my require, which is here. Going to run that just to make sure it loads. Yep, it's good. It's loaded what I expect to see. And then I'm going to go cut and paste this bit of code here. This is the answer. So you just have to kind of remember that this is the actual code, and what's above it when we pen it is the result of what's run. So I'm going to add a new cell, and see I don't have any result at the moment because I haven't run this yet. And then I'm gonna run that, and I can use this little arrow here to go and have a look, and you can see I've got some raw data in there now, so you can see these values come in, and you can start to see this, the start time, the end time, what the interval length is. These are just encoded dates. So this is the number of microseconds since January 1st, 1970. It's called epoch time. And we kind of have confidence at this point that we know that the data's loaded, and we can begin to manipulate it and do things with it. And that's basically the kind of like, since I put this in the footer of my project, it kind of gets all this stuff out of the way, because without the data, I can't really do very much. So I've put it towards the bottom. That are built into Observable HQ. And again, I'm referencing objects. So this VL, mark line, and render. That's coming from this Vega library, which is here. So I'm going to just replicate this in my new notebook so that we have that available to us. So now we've got the ability to do some graphs, and there are other graphing libraries available in the Observable, some really interesting ones. Allows you to really put some very nice looking graph elements together, along with animations and interactive graphs, so that you can select select off of the graph data. So now we'll be able to copy and paste this into the new notebook here, and notice I've got my data.data and, or sorry, my energy.data, and we're going to be referencing that my energy. And there is a method called data that's in here, which will return the data. So pressing this, we should get a graph. And thank goodness the live demo stuff is all good. Now, just to explain what happened, we've loaded our code, we loaded the library, then we went off and retrieved from a server, retrieved the data associated with the token. This is a test one. And now locally we have all of this data, and we can begin to analyze and work with it. So some of the power of what we've created is in the summarization and calculations of this energy data. This graph's not particularly that useful as it is. It's kind of just generally showing us that we've got probably reasonable numbers, 3 kilowatt hours within a half hour, or sorry, 3 watt hours, or 3 kilowatt hours of the 1,000 is a reasonable number for the household. And you can see it hardly ever falls to 0. So there's always this baseline. See, you know, the graph's always, there's something above it here. So what we want to start doing is summarizing this data and start to look at things like half-hourly profiles and summarizing those. And so we've created some helper functions. And we've got some documentation on this. But we've got these methods where we can look by so if you think about 48 slots, so 0 through 47 for the day. So you just index by, that's midnight to 12:30 to midnight 12 o'clock till midnight 12:30 is the start of the day. That's index 0, and then 12:30 to 1, 1:30 to 12:30 to 1 to 1:30, and so on until we get to the end of the day, where the last entry in here is going to be 11:30 to 12 p.m. Just before the next day. And then down the side, what we're getting the 7 days. So 0 corresponds to Monday, and 6 corresponds to Sunday. And when we're asking for this data, we're basically creating a sum. Okay, so I'm just going to add that in here, and I'm going to run this cell, maybe. I think I copied and pasted it in the wrong way here, so we can actually just type it in. So half hourly equals, another thing that's kind of interesting is when you start to type, it'll actually prompt you of what's available for you to select. So you can see all of the functions that are available there. So I've got things like, you know, by day of week, by half hourly slot, day of week, by month, etc. So in fact, we don't have to do exactly what we've done before, but we can now run that. Sorry, and I have to give it it's a function call. That's what these two parentheses here means. Call it as a function, and then we've got the data back for that. And likewise, we could graph it. We could analyze it further. This again is this is the sum of all of the data for the entire year. For this, so this is Monday 12. So Monday is 0. This first slot is midnight to 12:30, and that's summing all of those time periods up. We can ask for other things. So this will take other parameters where we could ask for the average, for instance. So let's go back to our worksheet. We can ask for things like, so by default, it's the sum, but we could say, I want the standard deviation, the mean, the max, the min, the median, etc. These are all more useful functions. So in this case, what we've done is we said, all right, I want to run the same function, but I'm going to feed into it. I'm going to ask for, so let's call it average half hour and we get then that's a little more usable. We can also look at things like max is quite an interesting one sometimes. So we can start to see over the entire year, what was my maximum use for men. And yeah, hardly ever goes to zero. Usually, if I see zero as a energy use, I'm skeptical that that's reality. So you can kind of get the gist of what that's doing. The next built-in thing that we have is like running a little bit larger profile. So this is taken from some literature. We didn't come up with these necessarily, but they're actually fairly intuitive. I mean, you could imagine if you were designing something to analyze how you're using energy, you would want to know things like, what's my average daily? So this is all days. So if I think about just generally, are you a high or low user? Your average daily gives you a pretty good understanding of that. If you're looking at things like averages, you really want to be also considering, do they vary a lot? So that's what the variance is doing, is saying, is this typically, are all the days looking the same? Or do you, throughout the year, and this is for a whole year worth of data, so you're probably going to see quite a lot of variance for a whole year's worth of data. And then we have something called a baseline, and baseline is looking at those minimums. This is the non-zero minimums, and this is sort of those ghost loads that are in houses that are either appliances that are on all the time, things plugged in like clocks, televisions. So they're small, usually small loads, and you can see that that's pretty well reflected in the fact that they're sort of 100 watts. So there's about 100 watts of ghost load. And what just to explain what's happening going this direction. So as we go down, this is week by week. So this is my average daily for, and let's zoom out. This is my weekly profile. So I've got 4 pages of this. If I flip, this is week 0. So this line represents, I think technically it's like December 27th or something like that, to January 5th and January 4th. And this is then looking at the average daily for that week. We can then start to look at the weekday versus the weekend. So if there's big differences between the weekday and the weekend, it's typically occupancy patterns. So that's, remember, we're looking at behavior here. So if you are home or not home on the weekends. Again, just as we look at averages, we also are interested in things like variance. And then we can break down the periods of the day. So we've got day use versus evening use versus off-peak use. So we break down three periods of the day. And this helps us understand, if you look at these dynamic prices, for instance, they're typically cheaper overnight. The kind of off-peak is most typically that overnight period. The day is typically up to about 4:30 in the afternoon, and then evening is at 4:30 to midnight region. And it's the most expensive typically, especially during the weekdays. It's most expensive. There are lots of theories about how that is going to change. I mean, it's market driven, so as demand profiles change, as we get more electric vehicles on the grid, we get more people with solar panels, etc., all this stuff will be dynamically changing. So this gives a good set of statistics that we can use to help profile the consumption to make it fit with the right tariff, and also be able to compare it to other households and do things like normalizing the energy. And then I put a little bit of extras in here where just to show some of the other functions being called. Again, I'll let you do these on your own, but it's things like histogram, so understanding, you know, what's the frequency of values, and I've got kind of like a center line here, which should correspond to this is about 300, 350. That should correspond to my average. My average will be maybe a little higher because it's weighted, but you know, you can start to see what's my most frequent consumption half hour by half hour, and that's quite interesting, because what you want to start to do is move this, you know, down and optimize around a kind of low flat consumption pattern. And then we have other interesting graphs that we can really quickly, and this just shows the kind of power of our library, is by just saying by month, I actually then get a breakdown of 12, you know, a summary of the 12 months. So we can even go back and do that over here and just sort of have a quick look and say, all right, I've got this main consumption pattern. I've broken it down to half hourly. Now let's do it by month. So month equals, and then all I have to do is say my energy dot, and then we've got all these things here, so I can say by month. I can run that, and you can see I have these timestamps, and then I've got this average, or sorry, the total amount for each of those months. So 0 being January. Well, actually, it's the timestamp, so I don't know. I'm not sure what that is. It's probably February. And some of the things like the library here will help us. Actually, it's March. So it helps us interpret complicated kind of internal data like these timestamps. Some of these graphical libraries, you know, understand what these things are, and they turn them into words that are understandable. That's what that T means, is to interpret this as time, and this is a quantitative thing. So I'm just going to quickly shoot through the next example, because we've talked a lot about energy and how the library works and how the summaries work. Let's go move on to sort of the tariff calculations. So we've got smart tariffs loaded in. We've modeled basically flat rate tariffs, time of use tariffs, and these are these kind of variable, dynamic or real time, and we have static time of use. So the difference being, on a static time of use, when you sign a contract for an energy contract, it says, okay, between the hours of, it's like economy 7 meters. So between the hours of, say, 10 p.m. and, I don't know, 2 o'clock in the morning, every night, you know that the price will be 5 pence per kilowatt hour. And during the day, you'll have a day rate, you know, which will probably be more expensive, something like 12 pence per kilowatt hour. Those are fixed for the duration of the contract. So you always know from the overnight time period and the daytime period that you've got these rates are locked in. Whereas with a dynamic pricing, it's this sort of agile concept where it's always changing. So it's tracking either the wholesale market or some kind of kind of variable component that the energy company is passing on to you, which means there's a lot more risk to you as the consumer. So in their tariff objects, it's just like what we've done with the energy. I've tucked all this stuff again below in the bottom. So I've created the two things we saw before. So there's the main object that we were working with. I've loaded some energy in, and we're now interested in things like tariffs. So I've just decided, just for illustration purposes, to create a tariff here to just show you what it looks like. So this is a flat tariff. It's got a start time. So this start period is typical. A contract will start on a particular date, has a unit rate associated with kilowatt hours of use, and then we've got typically standing charges, and that gets then encoded into again another kind of internal object that can be used by our libraries. And the structure of the tariff is what's probably the most interesting. In a flat price, it's only really two things that are driving the cost. So it's the unit rate and the standing charge. And then when you look at a time of use tariff, again, we're going to create one. We are going to be giving it something like a time to start and a time to end. So this is like my day pricing versus my evening pricing or my night pricing. So I have to shrink this back down a little bit. And then I have a value, so you can see this including VAT value of 9.5 pence is my sort of midnight to 6 a.m. and then 6 a.m. to 4:30 p.m. is priced at a higher rate, so it's 14.2, and then my peak, so this is 4 p.m. to midnight, is priced at 24.7 pence. And creating that, what happens is I get this then schedule, so I can see for each half hour, I can see what the price is, and I can see that the price changes at that point in time. So all I'm doing in this table here is I'm saying, okay, I've created this time of use tariff up here, and I'm just going to put it in the table so they can see it a little bit easier. And then we have there's some things that help, because some of the kind of time of use tariffs are not necessarily structured in exactly that way. So this is just a little example to show that you can span different times. The really interesting one is when we have dynamic tariffs. These are the ones that are changing every half hour. And this is something that gets loaded. So again, we're doing a new tariff, just like before. I'm now going to load it from the server. And I've got two interesting pieces to that, loading it from the server. I've got a name, so this is the Agile Tariff, and I've got what we call a GSP code. Now, GSP code is basically a regional, so London prices are different from, say, prices in the Midlands. And that's because the distribution companies that own the wires in the ground charge different rates based on regional differences. And historically, there were 14 regions, and they have letters of the alphabet as well as numbers that correspond to defining what those regions are. When we're using your smart meter data, So if we're sourcing your smart meter data, we know what that region is, so we can tell that. You don't have to go in and sort of code it in. And then select basically the tariff, so the prices that correspond with that. And what I've done is I've loaded those in. You can see the Agile pricing varies from anywhere, some of the peak prices that we've seen have been 35 pence, so they're very, very expensive compared to what you might be used to paying. But on the other side, you can see, April, June last year, I guess, there was a price event where there was negative 10 pence. Now that sounds pretty attractive. So negative 10 pence is you're paid to consume electricity, which is sort of an amazing twist in the way that the wholesale market works. But if there's capacity that needs to be, distributed out, they will actually pay consumers to use it. It doesn't happen often.
Josh, we've got about 15 minutes of presentation left before we go into 15 minutes of questions at the end. So just giving you a little countdown. Yeah,
no worries. So, so this sort of dynamic graph you can see is being loaded. It's again, it's 19,200 data points. So it's a lot of data. We can even go in and have a closer look at that, so you can see these rates. It's even more than that, because I'm loading even more history than just a year, and I'm loading all the way back to when Agile began. So you can see these rates in pence that are there. You can see the name. You can see it's a dynamic tariff, and we've got things like standing charge and stuff. I've got loaded in as 0, but normally we would fill those in. And what I wanted to then jump to is if we have all these flat rates, we've got the time of use rates, we've got dynamic rates, we have these three different rate types. You don't want to be programming these by hand. We have a database of these, and we've anonymized them, but they are real tariffs. Most of them are from Octopus because they have easy ways for us to grab those, and we're basically exposing those through these tools that we've made in such a way that you can say, all right, go get all the products. So I'm doing my new products, loading them. I'm now listing them, what the results look like. And you can even see inside, are these, so these are sort of like flat rate versus if I go to Dynamo, that's a dynamic rate, versus something like pair EV faster, which is going to be a time of use. So these are the 3 different types of tariff structures that we know how to deal with. And I've just sort of listed them out here in the table. Again, this is just an easy way to print them out, but it's the same as the code that's in there. What then becomes useful is to be able to use these products and tariffs to do things like calculate the cost. So just some example code, we're loading up the products, loading the tariffs. We're also loading, we could filter on supplier. So if we said, all right, because we've got suppliers in our database as well. So you can see we've got a number of suppliers which are sort of been anonymized. So this one's banana, and we had pear, and we'll have sage, thyme, rosemary, corn, etc. So you could say, well, I only want to see certain suppliers because I'm only interested in maybe ones that have a high high rating, and the supplier ratings and things are actually embedded in here. So we're grabbing this from Citizens Advice. We're looking at an overall star rating, some of the kind of billing accuracy and things like that are rated by Citizens Advice, and they update these monthly. So it's quite a good way to filter based on low. If you're wanting a high service or a very particular type of service, you can use these attributes to filter on suppliers that will then only show the tariffs corresponding to those suppliers. Then we're doing things like loading energy, and again, this is my energy. We did this in the previous examples. There's not anything particularly new there, although you might have not been able to quite keep up with what was going on. And we're taking my this annual energy, so this, and we're saying, well, this is my predicted energy. Now, remember when I was doing the EV up and down and the shifting, what I was basically doing was I was manipulating that predicted energy attribute. So I was saying, okay, we predict now with an EV that you're going to have this high load during certain half hours. And you can imagine that with these dynamic tariffs that are changing every half hour, that's going to be a big difference of when during the day is that consumption increased. And then by going through and associating all these things, I can then start to calculate an annual cost for each of the products that's listed here. Now, I will, before we even get into the details of this, admit this broke this morning, so it isn't actually going to be there, but it will be fixed. It's something that's working on the website, but we're incorporating things like the rate and all that. And normally there would be an annual, when we run this annual cost function, it's calc costs, it puts an annual cost onto to the object, and it's broken at the moment. So that would then give us the ability to sort these and say, okay, which one's the cheapest one? Again, we could do things like filter, and some of the stuff that we're exploring now into the tool is the profile that I showed you, that complex profile. So with my baseline, my overnight usage, etc., is to fit that to both low carbon technologies like EV, solar panels, etc., and the tariffs, to have the three elements then working closely together to optimize my cost. I'm gonna kind of leave it there. These examples are online; they're publicly available. All the code's there. We're going to be publishing more material about how to use them. Hopefully, it'll be pitched at a level that people without all our programming skills will be able to still utilize them. Yeah, we're looking for feedback from anyone on usability of the smart comparison tool, as well as the kind of code and things that we're open sourcing underneath it. So please feel free to chip in at into those projects. And hopefully there's enough signposting of where to put feedback that's obvious to you. So I think I'll kind of stop there and open up the floor to questions.
Josh, it's Nigel here. Thank you very, very much for that. Very informative, particularly that last bit. It's something that I've been wanting to do for quite a time. As a consumer going onto cost comparison sites, they always say, what's your average use? Yet I know that I'm not an average user. So something like that's going to be really, really useful for me. So thanks for that, and we will open up questions. So as you can see up there, there's the little question mark box thing up there. We've got one question in already, which is from Raj, who says that earlier in the beginning of the presentation, Josh, you mentioned that there were around about 19,000 data points. But if the data is coming in every 30 minutes, what's the difference between that 17,520 and the 19,000? Sorry.
So I think it's 19,200 is what we get. So we're getting something like 13 months worth of data rather than actually 12 months worth of data. So that's when we talk about, I guess, what the meter stores. That's what it is basically. So it's 48 times 365, but a little bit more.
That's great. Thank you very much. Hope that's answered your question there, Raj. So we'll await anything else coming in. Yanis, have you got any questions for Josh? No? So where do you see this sort of developing, Josh, in the longer term? I mean, at the moment, it's very much a developer tool. Do you see it becoming a consumer comparison tool?
I mean, this website that I showed you, this is the sort of embodiment of it. This is going to be, I mean, it's being put out to the public now, so it's usable. You can use it with your smart meter. We're going to be, maintaining this for forward from March and adding real tariffs into this. So at the moment, there are just, kind of hypothetical tariffs, and that's for proving the model out and making sure that government's happy that we're calculating things correctly, and they're going to kind of put their seal of approval on it. And then I think this will go into something like either the Carbon Trust or consumer advice or citizens advice as a comparison tool, so that people can actually use their smart meters and compare them with real tariffs that are out on the market. And we think then, once that's kind of the obvious use case is for purchasing, but the next one's going to be then, I think, around cost benefit of low carbon technologies. So if I'm interested in getting an electric vehicle, I really don't know what the impact of that's going to be. I don't know how much that's going to cost me. So this is a kind of meant to help people understand those scenarios around heat pumps, around whether a heat pump's a good investment. Will it pay back if I'm on the wrong tariff? I mean, it's shocking when you go on some of these tariffs. If you don't pick the right tariff to fit the application, you can be paying 1,000, 2,000 pounds more per year than you would if you get a tariff that actually fits well. Just chiming in, I see Jason's put a question: is it free to use? Yes, it is free to use. So it's both free from a code and API standpoint. It's also free from the access to your smart meter data. So if you have a smart meter, or if you have people that that have a smart meter and they want to access the data, it's free to use in both senses. There's no marketing sign up or anything like that. We're not sure how the costs will be met in the future, but we have funding at the moment to provide this for free, and we hope that continues into the future. But yeah, it's free. Any other questions from? I'm not sure how many people are actually out there with.
I think we've got about 20, 30 people out there.
Oh, great. Well, it's good. It's not like being in the same room with people. Sorry, everybody.
It's a brave new world. Brave new world.
It's quite unsettling to be on this side of the camera, but probably you're feeling like you're watching television anyway. The other types of things that we're looking at, I think, are comparing how so people that are using your API for free, we have some people who we're working closer with, and they have batteries or they have EVs already, and they've kind of donated their data and their profiles to help us refine the models and sort of understand what the usage patterns look like. And we've been very surprised at how profound you can shift your energy. Like I know that they've invested a lot in technologies to do that. So they've purchased many thousands of pounds worth of batteries or solar panels. It's not for everybody, but they are kind of the pioneers that are showing the way as to what's possible. And as the prices of those technologies decrease, and maybe shared ownership of those technologies, it does show potential for how prices can, suppliers and the pricing element can then adapt to fit that new technology so that everyone wins. The suppliers make more money, the consumer saves money, the grid.
You're right there, Josh.
Yeah, sorry.
There.
That's all right. My phone rings. The headphones are attached to it, and they take over, even though I put it on Do Not Disturb. But
got a question here from Elda. Is it possible to integrate customized tariffs into it, e.g., if you had an option to buy your energy from a community energy scheme?
Yeah, that's another good point. So we are looking at the potential to sort of encrypt and sign this data. So both on the tariff side as well as the your data side. And the idea would be is that as a community group, if you're producing energy, let's say you've invested in a community solar project or a community heat pump, could we show that that's actually putting energy back, or a heat pump wouldn't be putting energy back in, but a battery or something putting energy back into the grid, you could sell that. Could we make an internal market for that? And I think the key there is to make sure that the energy is not sold more than once. And as people talk about blockchain and things like that, but yeah, we really want to play with that concept of customized tariffs. You definitely can, and we think we'll have the ability to upload tariffs into the tool as well. That's helpful for running scenarios, not just to say switch to a new energy provider that would offer a tariff, but if you were able to model it as a community, then you could maybe see whether you would get payback for a community scheme. So if you had 10 people and said, okay, we'll have a hypothetical tariff that we load based on the demand profile of these 10 homes, would it pay back? So yes, we're really interested in that kind of peer-to-peer thing. And then Raj, I see your, I'll take the technically, where's the API retrieving data from? So we're hooked into a thing called the DCC. So this is the smart metering infrastructure, the national smart metering infrastructure. And we're one of the few companies we've had to fund and invest in hooking into this infrastructure. And we have then the ability to query the smart meters right down into the home over the network that those smart meters sit on. So the data doesn't sit in a database. It's when we're going to get it, we're going all the way right to the meter in the home, grabbing that data and then pulling it back through to the tool that I showed you. So it's there's quite a lot going on behind the scenes there. Yeah, and your point is absolutely true. So as we have more dynamic tariffs, the theory is that they'll become flat rate because the load profiles. So as people, it's not so much if they go for TOU or dynamic tariffs. It's when they get the technologies to flatten their consumption profile, or when they're using more overnight. Then the price will actually the wholesale price will start to flatten out because the consumption has flattened out. And so you're right. I totally agree. Time of use is something that is there to help protect consumers today. I think in terms of like knowing predictably what your price is going to be overnight, etc. Maybe there'll always be some differential. Maybe time of use will stick around and there'll be a differential. That could be due to things like wind and sun. So there'd be solar. But again, you could argue that if there's hydro power or pump storage or other battery storage in the grid, that again we'd see this sort of flattening out. So we're kind of looking forward to that day. The other scary thing is if people, or scary to the energy industry, is that if people start to self-generate, say they have solar panels and they're totally able to supply themselves, then there isn't going to be money left to pay for the wires in the ground because they won't actually be buying anything off the grid, so there won't be any revenue going back to the distribution companies. So there are some worst case scenarios where if everyone was off grid, who would pay for the grid? But we're probably a long way away from that scenario. There's also, I guess we haven't done gas either, so we do have gas data through the same API. I think that's also interesting when you're looking at things like heat pump sizing or other things like insulation projects. We are looking at some data sets to load into this tool to help. Tariffs aren't dynamic for gas. I don't know that they ever will be, but certainly the gas data is available as well as the electricity. I just happened to show the electricity in this particular project. Any other questions?
If there's no more questions, I'll do the judge's bit, not the judge's bit, the auctioneer's bit. Asking once, asking twice, asking 3 times. Okay. Thank you very much again, Josh. So what will pop up in a minute is the break slide with the networking comfort break rooms on, with the URLs on there, so you can either type them the laborious way directly off of that slide, or I did send that email around which has got the links in there. You can just click on there. So there's 3 rooms, red, green and blue, and that's so that as you can see that now, so that's so that there isn't sort of a melee of video and audio in those breakout rooms there. And I won't be coming in to necessarily tell to come back out again at 2:15. So it's up to you to get in, get out. You may find that you're stuck in a really interesting conversation there and want to stay in there. But yeah, thank you very much, and we will see you in a short while. Thank you very much. Welcome back, everybody. I hope you've had a time to recharge your glasses there. So I've got myself a nice cup of coffee in my University of Salford branded mug there. So this is the second session of this afternoon, and you've seen this morning from Josh, or the first session from Josh Cooper, about the data and how you can use it and manipulate things. So what we're going to look at now is, once you've got that data, how do you actually make kind of something useful out of it? So we have Carolus here from Evergreen Energy. I won't try to pronounce his second name correctly. I'm sure he'll do it for us. Carolus is head of the smart home at Evergreen Energy, and previously founded Homely Energy, a smart thermostat company integrating heat pumps with variable electric tariffs. So Carolus holds a BSc degree in economics and is currently completing a PhD in power networks at Manchester University. I guess you may have finished that now. Carolus, his PhD research is looking at the UK wider impact of heat pump uptakes on electricity prices. He has previously interned at Goldman Sachs in sales and trading divisions, spending most of his time in the commodities team. So without further ado, I will hand over to Carolus. Thank you.
Thank you, Nigel. Can everyone hear me now? Yeah, all good. Great. So I think for the introduction, that was really good. Thank you. So as Nigel mentioned, I previously founded Homely Energy. Homely Energy was founded in around 2018 with the intention of connecting heat pumps to variable electricity tariffs. And this summer, we've been acquired by Evergreen Energy. So I will go into a little bit of detail of what Evergreen Energy does, but that's the kind of journey. As Nigel mentioned, I did finish my PhD in power networks, and the PhD was on modelling wholesale electricity prices in the UK and seeing what kind of impact they will have when we're in 2030 and we have a lot more power being produced from renewable sources, such as wind, solar, and what could be done better. So can we use dynamic tariffs to reduce the impact, reduce the peaks of the demand, and make sure that we're utilising our networks in the most efficient way? Just a quick session overview. So I'd like to start off to just explain what Evergreen Energy does, introduce electrification and dynamic tariffs, introduce heat pumps. I'll then talk a little bit about how Homely controls are different from different control strategies, and then I will cover the trial that we did at Salford University. And the last bit of the presentation, we have an Excel sheet that is a simplified version of what we do, but it can give you a chance to play around with it and try it yourself. So first of all, just a little bit about Evergreen Energy. Evergreen Energy was set up with an aim in helping the UK achieve its carbon ambitions. Just as a quick overview, we're an installer of renewable heating systems such as heat pumps. So we have our own installation part of the business. We're making these systems more affordable through an assignment of rights proposition, reducing the cost of the heat pump to the cost of a replacement boiler. We provide support, advice, and design tools for 35% of all MCS installers in the UK. We're also the makers now of Homely Smart Thermostat, smart thermostat that was specifically designed for heat pumps to make them cheaper to run and connect them to dynamic electricity tariffs. And a little bit of background why we're here. Manchester is aiming for net zero by 2038. To achieve this, we will have to see a significant change in the way we heat our homes, moving from predominantly gas boilers to a combination of electric heating, including heat pumps, district heat networks, and hydrogen. In this workshop, I'll go through some of the problems associated with the electrification of heating and how a combination of smart technology and tariffs can help us overcome some of these. A few numbers to get us going. So National Grid estimates that around 180,000 heat pumps are currently installed in the UK, with the potential of increasing to 12.5 million by 2038. That is quite a huge number. That would be equivalent to around 600,000 heat pumps a year. Numbers. These are numbers from National Grid future energy scenarios. You can look them up. I think these were from last year. There was an updated version of the future energy scenarios, but I haven't had a chance to update these numbers just yet. And in addition to this increased uptake of heat pumps, increased electrification, we're also seeing the power generation side of the market changing. So we're moving away from fossil fuels and we're trying to produce more power from renewable sources such as wind and solar. So you can see how throughout the years that the amount of power that we're going to be producing from solar and wind is going to be increasing significantly. Now, even though heat pumps are a great way of reducing carbon emissions, nearly 2 tons of CO2 can be saved per heat pump per household per year. There are some limitations in what we currently do, what we could do today with our current electricity infrastructure. We can just imagine if we were all going to install a heat pump tomorrow, meaning that 12.5 million heat pumps, for example, were to go online at similar times of the day. This would mean that additional load would be we would try to push that additional load through our current infrastructure of the power networks. And heating is not the only thing that we're trying to electrify. So we're seeing an increased uptake of electric vehicles, and all of these additional loads for all of these additional loads, we need to make sure that our infrastructure is suitable. Alternative to building new power plants to sustain this increased demand, we can do smart control, and this is what I would like to be talking about today. So by using smart heat pump scheduling and smart vehicle charging, we can smooth some of these demands throughout the day and shift the consumption of electricity to periods of high renewables. So when wind is available, we can shift more consumption to those periods. We can also reduce customer bills and the need for network reinforcement by using the electricity when the production of it is cheaper, increasing the use of that green electricity. Just before I give you some examples on how the electricity prices look throughout the day, I wanted to have a brief introduction into how domestic electricity prices are structured in the UK. This is an infographic from Ofgem, and as you can see, the wholesale electricity price. So wholesale cost of electricity is the cost of electricity as is produced by the electricity producers. And we can see that it only constructs a fraction of the domestic electricity bill. So in this example, you can see that it's only 32% that it accounts for from the actual domestic electricity bill. The other components are network costs, other obligation costs. Just as an example, Agile Octopus, dynamic tariff in the UK by Octopus Energy, for my particular area, charge a premium of 12 pence per kilowatt hour for the consumption of power during the 4 till 7 period, and that is to account for some of these variable network costs throughout the day. And to move on to some examples, so in front of you, you can see a particular day in the UK when there was a lot of wind, and that caused electricity prices to go quite a bit lower. So Octopus Agile is the dynamic tariff in the UK that is reflective of the wholesale prices of electricity. So whenever there is low demand, high production of power from renewable sources, we can see those prices changing and reducing. In this particular case, throughout the night, we can see that the price of electricity was actually negative. So people were paid to use the electricity, and that was because the wind power production was very high. And throughout the night, the consumption of power is much lower. In this case, all people, our customers with homely thermostat were able, those heat pumps were automatically turning on to consume this power during those negative price periods, so they were actually being paid to heat their homes. It's not always as good, so prices do vary, and you have more expensive days. And an example in front of you is of a day with a low wind. That was again in 2019, and as we can see, the price of electricity throughout the night was quite a bit higher in this example, around 10-11 pence. There's not to say that homely cannot still provide you with benefits, as the thermostat would anticipate what this electricity price is throughout the day, and it would try to pick out these cheapest electricity points to make sure that the heat pump is running, and whilst making sure that it achieves your desired temperatures. Just before I move on to the next part of the presentation, are there any questions? Nigel, you honest? No? Are we all okay?
No questions come through yet. Just give it another minute or two.
Sure.
Calling it once, calling it twice, calling it 3 times. Carry on, please.
Thank you. So now I'll just go into a little bit of an explanation of what heat pumps are, because I'm not sure. I'm sure that a lot of people understand them, but just a brief introduction into what they actually do. So heat pumps are just a very efficient way of heating your home through the heat extracted from outside air or ground and delivered to your radiators and hot water cylinder with the help of electricity. As some of this energy is extracted from external sources, heat pumps are able to deliver around 4 units of heat throughout the year for every unit of electricity that they consume. That means that 3 units of that heat is taken from the external sources like the air or the ground and are absolutely free. In addition to reducing overall energy used for heating, and they can also reduce customer bills further when combined with variable tariffs and smart tech like the homely thermostat that make sure that the heat pumps are operated during the cheapest times of the day when the electricity produced is the cheapest. I thought just for the more detailed listeners, I can explain a little bit about how the heat pump actually works. So this is a reverse refrigeration cycle. It has 4 main components, which are the evaporator, the compressor, the condenser, and the expansion valve. The way that the heat pump works is firstly, the evaporator extracts heat from the collector and transfers it to a liquid contained within the evaporator called the refrigerant. The refrigerant starts to boil once it's heated up by the energy from the collector. The gas generated then moves to the compressor, which increases the pressure, which results in an increase in its temperature. This high temperature gas then travels to the condenser, which transfers the heat to the heating system. So here we would have the heating system. And the final step in the process is the expansion valve, which removes the pressure of the liquid, allowing the gas to convert back to liquid before returning back to the evaporator. And then the cycle continues. The reason why working with heat pumps is so much different than working with gas boilers is because of the way that the efficiency changes with the heat pumps. And this is just an example. So you'll hear me a lot talking about the coefficient of performance, or COP. COP is just the ratio between the heat produced by the heat pump and the electricity consumption. So as an example, a COP of 3 would mean that to produce 3 units of heat, your heat pump would need to be consuming 1 unit of sorry. This is from the technical manual of a heat pump that is installed in the Smart Meters Lab at Salford University. And as you can see, the coefficient of performance of the heat pump changes significantly, dependent on both the flow temperature of the heat pump, which would be these temperatures here. So the blue graph in this graph is a COP for the flow temperature of 35 degrees. The red one is going to be for 45 degrees flow, and the green one is for 55. Flow temperature here, what I mean is the flow temperature is the heat, is the water leaving the heat pump. So you can think of it as the water that is going into your radiator. So the hotter your radiators, the lower the efficiency of the heat pump. That's why heat pumps are work really well with underfloor heating, for example, where you can keep these temperatures very low to maximize the efficiency. It's not to say that they don't work with the radiators, it's just that they work slightly better with bigger radiators and or underfloor heating. And in this particular example, we can see that with the 35-degree flow temperature, if the outdoor temperature was 10 degrees, we would be getting somewhere around 4.5 COP of 4.5. So 1 unit of electricity going in would be producing 4.5 units of heat. If this temperature outdoors was to drop to 0 degrees, we can see that that COP would be dropping to around 3.5. So 1 unit of electricity only produces 3.5 units of heat. Just before I move on, are there any questions on the heat pump side?
Yeah, we've got a question from Raj. Just for the cost of ground source heat pumps goes quite high. I guess this is the thing. What's the maybe a question here is the difference between the air source and the ground source heat pumps.
Is this the difference in terms of the running costs or the difference in terms of the installation costs?
Probably a bit of both, and the efficiency as well, I suspect.
So in terms of the cost of the installation, ground source heat pumps are a lot more expensive to install. I wouldn't be able to say a ballpark figure because it very much depends on the kind of system that you're installing. So, but ground source heat pumps do tend to be a lot more expensive because you need to drill the whole you either need to put in the ground loop array or you need to drill the ground. In terms of the running costs with a ground source heat pump, if I move back to the slide before where the COP was dependent on the outdoor temperature, with ground source heat pumps, this is not so much of an issue because that temperature, the temperature of the ground stays fairly constant throughout the year, and therefore even at very low temperatures, your COP would stay fairly similar. Does that answer the question?
I think that's great. Yeah, move on, please. Yeah.
Brilliant. So I'll now move on to what Homely does and what it has been set up to do, what Homely does, and what kind of control things are we taking into account. So as I mentioned before, Homely was set up as a smart thermostat specifically for heat pumps. The reason why they're a little bit different is because our algorithms continuously learn how long it takes for the home to heat up and cool down, depending on how insulated the home is, how cold it is outside, how warm you want the house to be, but also takes into account the heat pump's coefficient performance, as I've discussed before, to optimize the running times and maximize the efficiency. Homely thermostat can cater for all types of customers. So we do have some customers that want to have standard control, which doesn't allow us to do more of the clever stuff that we're talking about here. But so standard control would allow the customer just to have a remote control of this heat pump. You can turn it on and off whenever he'd like. Smart control would optimize the heat pump operation for fixed tariff customers. So even if you're not on an Agile tariff, you can still install a Homely and you can control your heating using the fixed tariff. And smart tariff control is where we do all the clever stuff with in terms of the heat pump, and also add on the smart tariff. So it's scheduling the heat pump to come on during during the lowest cost periods. Just before I move on, so the point why you might want to install, even with the standard and smart control, why you might want to install Homely is because we can also provide the savings reports. So after we've learned about the house and how long it takes for it to heat up and cool down, what kind of efficiency of your heat pump is, we can then provide the customer with the savings report to say that if you were to switch to a smart control tariff, this is how much you could be saving. If you were to switch to a smart tariff, this is how much you could be saving. In this presentation, I'm also going to, in this part of the presentation, I'm also going to be running through a couple of simulation results in terms of what kind of savings we could be expecting using a heat pump with variable tariffs and with Homely control. Just before I go into that, I wanted to give a quick introduction in the assumptions that I've taken. As every house is different, the estimated savings would be different. The savings that I've calculated here are based on the assumptions on the screen. So this house is based in Bristol. The heating and hot water provided by a heat pump. I'm assuming a ground source heat pump with a fixed ground temperature of 5 degrees. We have a fixed tariff that we've considered as the alternative to a variable tariff at 17.745 pence per kilowatt hour. This was an Octopus 12-month fixed, checked February 2021. Just a caveat on this price, the Agile prices that we're using, they're actually for the year of 2020, but I was not able to find the respective fixed tariff for that was available in Bristol for 2020, the year of 2020. If you do, I think that the results that I will be presenting can still give you a rough idea of what the savings compared to this particular fixed tariff would be. But you can then, if you were to look for a different tariff, you can scale them whichever way to when you're looking at the fixed tariff. The fixed export is 5.5 pence per kilowatt hour, and we're modeling a well-insulated house with a 6 kilowatt heat pump with the area of 91 square meters. I will also just run through some of the stuff that we've done recently with inclusion of the PV and a battery. So PV installation that we're considering is 2.9 kilowatts, and battery capacity is 4.8 kilowatt hours with a max charge rate of 2 kilowatts and a max discharge of 2.5. Moving on, just in terms of what Homely can do right now, and what we've been doing for the past couple of years is we were controlling heat pumps. So our main area of concern was how can we make the heat pump run the most efficiently. And the first result that I wanted to present is just the optimization of the heat pump. So if you were to use Homely thermostat with an Agile tariff, we can see the comparison between the costs here. So with a fixed tariff, the cost of heating for this particular house over the year of 2020 would have been around £500. If you were to use an Agile tariff for that year, the cost would have almost halved. And this is nothing to do with Homely. At this point, this is just switching a tariff. And therefore, this is why I was mentioning that fixed tariff that are used for comparison. Just so that you can kind of take that into account when you're making decisions. If you were to add an Agile a Homely thermostat on top of the Agile tariff, this is where our thermostat can help. So in addition to the savings that you've already made by switching to a tariff, Homely thermostat can add an additional saving of around £77, which is around 30% of the heating bill for these customers. Now, recently, we've been working a lot more on trying to optimize the whole house, and these are just preliminary results. These are simulated results, and we haven't done real life installations where we have PV and a battery, but these will be coming online in the next few months. I still wanted to share this information because I think it's useful to just walk them through. And here what we're doing is we're trying to optimize the whole house power consumption when the house has different sets of kit installed. We consider other consumption as well as the heat pump consumption in these results. So this fixed tariff cost of £1,043 is the cost of electricity for the whole house. So all of your other consumption in terms of just a regular domestic customer, the heat pump consumption, all taken into account here. So as we can see, what we discussed before is that adding a homely thermostat on top of the Agile Tariff, that it brings a homely savings to around £77. If you were to install a PV and a battery, and this is where our homely thermostat would take control of the whole setup of the system, your fixed tariff would already have decreased to 631, even if you were on a fixed tariff. If you were on an Agile Tariff, this would decrease even further, but adding a homely on top of the system would save around £192 a year. Other things that we provide as part of the homely is as mentioned, the integration with the PV batteries and demand for response. That is all coming in the coming year. We do also provide remote monitoring and diagnostics. So we want to make sure that all heat pump installers, not just the Evergreen, but everyone else can use homely thermostat to track the performance of the systems that they install, to make sure that heat pumps that are being installed are installed to work in the most efficient way. And as mentioned, we also provide these savings reports, so customers that are using a thermostat in a standard mode, for example, would get would be able to understand how much you could be saving if you was to switch to a dynamic tariff. And the next couple of slides are actually just a bunch of graphs that I was trying to show how homely thermostat works and compare it to other control types for heat pumps. So usually the way that heat pumps were originally set up to be controlled is on a flow temperature curve, which means that when you install a heat pump, to make sure that it works at the lowest the highest possible efficiency and the lowest possible flow temperature. As you remember from the previous slides, the lower the flow temperature going into the radiators, the more efficient the heat pump will be. So historically, heat pumps were set up to operate on a weather compensation and basically making sure that that heat pump operates the most efficiently, which meant that it tracks the same temperatures throughout the day. So even if you wanted the house to be warm just in the evening and in the morning, the internal temperature of the house, if you were to install a heat pump and use a weather compensation, would be the same throughout the day. That would increase the efficiency of the heat pump, and therefore that is the more efficient way to control it. This example in particular is for people who wanted to have the standard thermostat control with a heat pump, and I wanted to show how this might not be the most efficient way to use the heat pump. So if we're thinking about a boiler, we know that whenever we install, for example, a rotary dial thermostat on our wall, it will turn on the boiler whenever we tell it to turn it on. That could be okay with a boiler, but with a heat pump, that will mean that our efficiency is reduced significantly. And in these graphs, a couple of information that some of the information that I will provide is the set temperatures. So in this particular case, we're assuming that this customer wanted 21 degrees between 6 and 10 o'clock at night, and 21 degrees between 8 and 10 o'clock in the morning. These were the times when the customer actually wanted the house to be warm. The internal temperature is the simulated internal temperature using the controls that we've specified over here. The second from the top row is representing the flow temperature of the heat pump. So this is the simulated flow temperature of the heat pump using the controls that we are providing it. The orange lines with the axis over here, that's the coefficient of performance. So we can see as the flow temperature of the heat pump approaches 50 degrees, the COP of the heat pump drops to around 2.5. And the bottom graph is just representing the electricity price in terms of Agile. So this was just a particular day of Agile. And this is overlaid with a fixed tariff that we were talking about before, which is 17.745 pence. There's also these periods where the heat pump is actually turning on. And as you can, in this particular case, we're saying that this customer just set up his heat pump to operate the same way as you would have done potentially a boiler, and said that I just want for the heat pump to turn on between 6 and 10 o'clock at night. As this thermostat is not anticipating the weather conditions, as it's not anticipating the actual requirements of the customer, we can see that the internal temperature that is simulated is not actually getting nowhere near to the user set point. In full power during the time when you want the house to be warm, and whilst doing that, it's reducing significantly the coefficient of performance. Just before I move on to the next slide, because there will be a few of these, 3 more of these to go, using different control scenarios. Are there any questions that I should answer just to clarify anything on these?
We've had a few questions in, but probably just on these ones, it's not specific to these. If we carry on and take them later on, I think that's the best thing to do.
Sure. Okay, so the first one, it doesn't seem like the standard thermostat control is an efficient way to run the heat pump, and we can see that this is for a couple of reasons. You're never getting warm enough, and you're also reducing the coefficient of performance of the heat pump, which means that you're not running it in the most efficient way. The second approach to the control of the heat pump could be that you install just a smart thermostat. So smart thermostats and other smart thermostats, they anticipate how long it takes for the house to heat up and cool down. And therefore, knowing that you're going to need the house to be warm between 6 and 10 o'clock at night, it would start operating the heat pump a couple of hours before, depending on, and the amount of hours that you need beforehand would depend on how cold it is outside. And this is what a lot of smart thermostats do, and therefore it would just click on the heat pump to start preheating the house before you actually get back home. A couple of issues with this control scenario. So if you're looking at the Agile Tariffs, for example, where the electricity price is the most expensive between 4 and 7 o'clock in the evening, that would mean that your heat pump is always running through those periods, or majority of the time is running through those periods. And also your coefficient of performance, again, is not being maximized. So you're trying to blast the heat pump as much as you can to make sure that those temperatures are achieved, which means that you're increasing those flow temperatures quite high, which means that your coefficient of performance is being penalized. So the next one would be just a homely thermostat working on a fixed tariff. This is very similar to what a weather compensation curve does, and this is confirming these results confirm to an extent that the weather compensation way of controlling a heat pump, not just with a homely thermostat, but actual weather compensation on the heat pump, could be the most optimal way to control it. I will show an example of where weather compensation curve didn't achieve the maximum comfort of the user, and where homely can still help. But the result that you can see right here is showing how weather compensation, so heat pump running for majority of the time throughout the day, is an appropriate way to run the heat pump to make sure that it's achieving the highest efficiency. So you can see how the coefficient of performance over here is reaching around 4, slightly changing towards the end of the period as the outside temperatures are decreasing, but all of these are maximized and the flow temperatures are as low as possible. So we can see here that the flow temperature curve is around 37 degrees during this period, maintaining that 21 degrees throughout the whole day, but increasing the efficiency there and therefore reducing the energy bill for this customer. And moving on to the variable tariffs. So this is where homely thermostat would take into account both the efficiency losses that are involved in raising the flow temperatures slightly higher than what they should be. So we can imagine that if we were to boost the heat pump operation during the cheaper times of the day, so like here or during these periods, we might need to raise the flow temperatures slightly higher than what we could have achieved with our weather compensation curve, as we've seen before. This can be taken when we're making these decisions. We can also take into account that that cost of electricity can be much cheaper. So, for example, heating your house throughout the night, even with a slightly higher flow temperature, might still make sense if the price of electricity throughout the day is much higher. So over here, for example, we can see that throughout the day, the peak just before the 4 p.m. was around 14 pence, and overnight the price of electricity dropped somewhere around 8 pence per kilowatt hour. And that's why we've increased our flow temperatures quite a bit higher throughout the night to overheat the house slightly, and then let it coast through the more expensive peak periods over here. This is also the case when we're coming to the 4 till 7 period. So as we can see, the price of electricity jumps dramatically during the 4 till 7 period, going all the way up to 30 pence per kilowatt hour. We can see how the internal temperature anticipates this electricity price. It still knows that it needs to get as close to the set temperature as possible, so as close to the 21 degrees that the customer has provided. But it's boosting that temperature indoors all the way up to 21.25 degrees, and that then uses this time to coast through, uses this temperature to coast through the most expensive period. And yeah, that's an explanation of how the kind of things that we need to be considering when we're controlling heat pumps. Are there any questions at this point that I could help with?
We'll leave it for a minute or two, and then before we move on, I know there was a few questions earlier on, which I think I've answered privately, but we'll give it another couple of minutes, Carolus. I don't know whether you've seen Carolus yet, so Dave, if you want to switch over to Carolus, you can. Mainly the screen's been on there. This is Carolus himself. Give everyone a wave, Carolus.
Hello.
Thank you.
I was thinking that no one can see me, so I was going to have a sip of water.
No one can see you at the moment. They're looking at me at the moment, so you can have a little sip of water if you want. We haven't had any new questions come in, so let's carry on with the. Oh, hold on, one. Yes, we do. Do you have typical installation costs to retrofit a typical Victorian house?
So you can actually get quite a good estimate using the Evergreen Energy calculator for the installation of the heat pump. And so if you go onto the Evergreen Energy website, you can put in a couple of some of the information about your house, and it will provide you with a quote how much it might cost, and also different funding options. So it will let you know about the Green Homes Grant, for example, that currently it gives you, I think, £5,000 if you're installing a heat pump, and also the assignment of rights proposition. So it could be that that will reduce the heat pump upfront costs quite significantly. Nigel, you're muted.
Oh, sorry. Yes, yes, you are muted. That's the phrase of 2020. There was another question about the insulation, but I'll pick that up separately. So please carry on, Carolus.
I think it is just before we move on. In terms of the insulation, I think it's if it's referring to how long you can actually store the heat in the house. That's a very good question, and basically the more insulated the house, what Homely is doing is kind of seeing a house as a battery. So what we do is just charge it up, so increase the temperature before the more expensive periods and let it coast through to the most expensive periods by kind of depleting this battery that we've charged up. The point being that the more insulated the house, the lower the heat loss is going to be from that house, and the more you're going to be able to shift the consumption to the cheapest periods. So you will be cheap. The higher the insulation that you have, the more of these cheapest pockets of electricity you'll be able to pick up. Okay. So moving on. This is the study that we did at the Smart Meters Lab quite a while ago now. I think it's around a year and a half ago, where we actually wanted to just test out what this proposition looks like and how, with some real data, show the kind of savings that we could be achieving. So I would like to show that the purpose of this test was to show that the weather compensation, even though it's great when using the fixed tariff control, it's not the most efficient way if you have the ability to be using the variable electricity tariffs such as Agile Octopus. And during the testing, we've presented that you can save around 20% by using Homely controls and combining it with a heat pump. Just to introduce the scenario, so the original control, this is where we're assuming that there is a weather compensation and that the temperature is set constant throughout the day. So as we've seen in the previous example, just to give you a kind of quick view, is this is what we're assuming. So we're assuming that because the weather compensation works best by keeping the temperature constant throughout the day, because it's minimizing the flow temperatures and maximizing the efficiency. This is our original control. So heat pump adjusts its operation according to the outside temperature. Weather compensation being that the colder it is outside, the higher the temperature in your radiators will need to be. Set temperature does not vary throughout the day. So as we've seen, we're keeping it at around 21 degrees. And the price of electricity is not varying, so you have a fixed price of electricity throughout the day. If you were to then consider our scenario, so Homely plus Octopus Agile, we can see that a heat pump heats the house during the cheapest periods, and these periods are chosen by Homely by estimating all of those different parameters. We have multiple set temperatures, so majority of people, at least before COVID, had two periods that they set up their houses to be warm at. So one is the morning, 6:30. In this particular example, we use 6:30 till 8 o'clock. So just before you go from work, you want the house to be warm, and then you want the house to be warm when you get back from work. So 6 till 10 o'clock at night, and we had the same temperature as before, 21 degrees. The prices that we've used in this example were Variable Octopus Agile. Just to introduce some limitations of the testing that we did here, these tests were not performed under controlled weather conditions. So one difficult part of comparing the operation of the heat pump using different control strategies is that we don't have the exactly same day, two exact same days that are consecutive. Energy House will, but we in the real world do not have the ability to have the controlled weather conditions. And in this case, because we were doing the test in the smart meters lab, we decided to choose a cooler day for the homely controls and a much warmer day for the original controls, the weather compensation. This is to make sure that just even starting the experiment off, the homely controls were being penalized. So if we can achieve the savings even with this limitation and on a much colder day, that means that there is something there. So to explain which days we've chosen, as I mentioned, homely was working on a much colder day. So we have 3 degrees during the night, reaching around 9 degrees throughout the day. For the original control scenario, so weather compensation, we were using around 9 degrees during the night, reaching all the way to 12 degrees throughout the day. So we would, before we start this off, we would expect that homely, if we were to operate the heat pump using the same control strategy, during the homely day, it would have cost us more than during the original control day. Now, looking at the controls, and this is the original control scenario. As mentioned, it's working on the weather compensation curve. So we have the set point of 21 degrees, and we can see that the temperature was slightly decreasing through time. The reason why for this deviation from the set temperature is that the weather compensation alone, sometimes you need to spend quite a bit of time in adjusting the way that the flow temperature is reacting to the outside temperatures. And if this is not configured correctly with the weather compensation as it is on the heat pump, if it doesn't see the internal temperature, it might not be getting, it might not actually be achieving the temperatures that you've desired. So in this case, 21 degrees. This is where homely thermostat would look at the weather compensation as well as the internal temperatures. And that's why we would be able to achieve the much closer alignment to the 21 degrees. As an example, here we were using electricity prices of 15 pence, and this was found during the same time as the Agile prices. We can see how the heat pump was operating throughout the day, turning on and off, and kind of trying to maintain that temperature as close to the set temperatures. Now, with the homely control, similar to what we've seen before, throughout the night, it was trying to heat up the house as much as it could to kind of store as much heat as it can before the morning period. So when we got up in the morning, and then throughout the day, it slightly overheated the house to make sure that it can turn off when the electricity prices peak, and then coast through those temperatures before the price of electricity reduces again, and then turn the heating back on to make sure that it's maintaining that temperature between 6 and 10 o'clock in the evening. From the results that we found here, so we were comparing just the 2 days, but the original heating control scenario would have cost us £1.57, and with a homely control, this would have reduced to £1.26. So in terms of conclusions from this very simple test, we have shown that even on a much colder day, homely controls with variable prices were able to achieve 20% savings. This is whilst achieving more comfortable internal temperatures as well that better match the user set temperatures. So this is just back referring to the internal temperature, so the orange line on this graph being closer to the set temperatures in homely controlled scenario when compared to the original controls, where the internal temperature actually deviated by up to a degree towards the end of the test. Do we have any questions at this point?
Nothing specific that we can answer. I'm just looking at another question I think I can answer privately here, but yes, carry on, Carolus.
Sure. So this is the end of the main body of the presentation. I would like to, if you have any questions, I would like to answer them now, but we do have a simple simulator, an Excel-based simulator that everyone can download and can play around with trying to schedule their heating the way that, well, trying to schedule their heating during using the cheapest prices. On the screen, you can see the link to the website where you can find this Excel sheet. The password to access it is Salford. I think if it's okay, Nigel, I'd like to wait for a couple of minutes just to see if there are any more questions, and then let everyone download the Excel sheet if they'd like, and then walk them through how the Excel sheet works.
The only question that we've had come in is just to do with some costings things, which I've kind of answered. But yeah, wait for a bit. So I've got a question for you. So you're looking specifically at the domestic sector here, I guess, is the main thing. What about commercial sectors with regard to, say, the University of Salford? It has maybe electrical. Some of the new engineering building that's going up, for example, is entirely electrically heated. And one would imagine that's on heat pumps. Would you and Evergreen look at that kind of market, the more larger commercial buildings, as opposed to the domestic home market?
Very good question. When I started off Homely, and the concept of preheating your house during the cheap times is not new. It's been around for many, many years. We've used storage heaters, for example, for many years, using the energy from the night to heat the house throughout the day. To answer the question in terms of domestic and commercial, when I was doing my research before I started Homely, it seemed as though the home energy building energy management systems for commercial sites was quite a saturated market, and there were quite a few people that were trying to do this kind of stuff for commercial buildings, and domestic sector was the one that was kind of neglected. So that's why we started off with the domestic sector. I'm not sure if it's something that we would look into in the future, but at this point, it's not something that we are looking into to control the commercial buildings, although the potential savings for a commercial building owner are huge.
Thank you very much. Please carry on.
Sure. So I'm going to switch from the actual presentation just to my Excel sheet. So I'm assuming at this point everyone had a chance to download the Excel sheet. Just to show, I'm just going to quickly run through how to download it. So if you go on to homelyenergy.com/workshop, you should receive this guest area part. If you type in Salford, you should see an Excel sheet that is available here. If you click on that, that should allow you to download it. Place. I'm going to open this Excel sheet as well and try to walk through kind of what we're looking at here. This is a very much simplified version of what we're doing, and it's just for graphical illustration of what we're trying to achieve, as this doesn't take into account coefficient of performance, it doesn't take into account flow temperatures, and it also doesn't take into account that with some systems there might be lags in terms of when you turn on the heating and when the heating is actually starting to impact your internal temperature. But for the purpose of just seeing how the costs compare, we thought that it was quite a fun thing to play around with. So in the Excel sheet, a couple of parameters that you can set for the specific system is degrees rise in half hour when heating. So if you were to turn on the heating for half an hour, how much would your internal temperature would be impacted? Here I assume that it would be 0.3 degrees. If you were to turn off the heating, this would be the time that it takes for it to actually, how long does it take for the temperature to drop during the half-hour period? So we can see that over here, this is our data, this is what we can play around with. We can see that once the heating is turned off, the change in the temperature during the half hour is actually half a degree. So from 21, if the 21 degrees is the starting point of our internal temperature, in the next period is going to be 20.5. The other thing that we can consider here is the heater size. So what is the power input of the heat pump? Here I've assumed 1 kilowatt. It was just to have a rough figure of what it could be. You can also select a date, and I will delve a little bit deeper into what this is actually doing later on after we've had a first go in trying to optimize the heating using this calculator. The results that are coming out of the changes that you're making over here is the total cost of running the system. So in a single day, how much would you be paying using the Agile Tariff? How much would you be paying using the fixed tariff? And what kind of savings in terms of percentage you'll be achieving. Graph over here gives us the information on the Agile prices that we're working with, and these are reflected over here. So prices pence per kilowatt hour. The fixed tariff that we're using for this simulation, so we've assumed that the cost of electricity is not varying, and it's 14.6 pence per kilowatt hour. The set points, we've assumed that you want the house to be 21 degrees between 7 and 9 o'clock in the morning, 6 and 10 o'clock at night. And then the actual changes that we could be making is in the heating columns over here. So we'll be able to change when we're actually heating the house, and that will have an impact straight away in the actual internal temperature that we're seeing over here. Then we can see the changes in temperature, the temperature that is the actual temperature that we're achieving, which is the orange line. The cost of electricity, so this is just the multiplied value of the heater size in kilowatts times the prices of electricity as per Agile. And we also have a fixed cost for heating during that period using the fixed cost. Using the fixed prices, so using the 14.6 pence per kilowatt hour. Now what I would like, if you're interested, what I would like to do for you to do is try to figure out how to get the savings at the highest that you can using the electricity prices and trying to turn the heat pump, turn the heating off during the more expensive periods and trying to just capture those periods where the prices are the cheapest. I'll give you 5 minutes just to play around with it, and then we can I can show you as well how I try to do it. Welcome back. So I hope you had a chance to play around with the simulator, but this is what I got to. Probably I'm not sure if anyone else got more savings than I did whilst achieving the similar temperatures. So it would be interesting to see in the Q&A if anyone managed to do better. But basically what I was trying to do here is kind of avoiding the more expensive periods in the morning, trying to make sure that I'm dumping as much heat into the house as possible during the night, and then also trying to avoid this most expensive period between 4 and 7, and again trying to just heat the house up as much as I can throughout the day to make sure that I have enough heat to coast through the most expensive period while still staying fairly close to the set points. Given these assumptions, it seems as though my fixed cost operation would have been around 1.9 pounds per kilowatt, 1.9 pounds for this day. My variable price would have been around £1, which would achieve around 43% savings. Now, a couple of things that we also need to consider is that, and even though we know that the electricity prices are going to be much cheaper, for example, between the 4 till 7 period, so sometimes we might be tempted to just always turn off the heat pump during the 4 till 7 period and then operate in the same way throughout the day. So we know, for example, that during the night the prices are going to be cheaper, during the day the prices are going to be cheaper. There will be a period that is slightly more expensive in the morning, like we've seen over here. But apart from these, the prices tend to be cheaper during the different periods. So we could just say that let's run the heat pump during this time, so just before we get up. Let's run the heat pump all the way throughout the day, and then let's turn it off during the 4 till 7 period, and then this increase in price during the morning period. The problem with that control is that if you were to do it on this particular day, for example, you would have been fairly close to your set points. But let's say that this day was slightly more cold, and we can see how that completely changes the way that your internal temperature is behaving. So by changing the day from 0 to 1, we can see how the degrees rise in half hour and degrees fall in half hour have changed, and that has impacted the internal temperature readings for this property. So now what you would need to do is you would need to try and re-optimize that control yourself in terms of to make sure that you're still achieving those temperatures that are close enough to the set points that you've requested. In terms of the homely, we take all of that into account, and given the electricity prices and the weather forecasts and the flow temperatures and the COP, we figure out the most efficient way to operate the heat pump. That is all from the interactive part. If anyone is interested in terms of to learn more about homely and how we're controlling stuff, please do get in touch. We do have I'll just pull up the information slide for us. So yeah, I saw that in the Q&A there were quite a few questions about the cost of the heat pump installation, and all those kind of questions we can answer. So if you get in touch with us at hello@evergreenenergy.co.uk, or just give us a call, we'll try to provide as much information as we can. Thank you.
Thank you very much, Carolus. So we're now at the end of the session here. We will take some more questions, end of session questions from anybody. So yeah, please type them into the Q&A box, which is up there. Some of you have discovered it already, some of you probably haven't. So this is a quick question while we're waiting for something to come in for you, Carolus. So I've got you're obviously a heat pump man, yeah. And my background is in wood fuel and wood stoves and things like that. And my way of sort of controlling sort of cost and spreading the load is that I put a few fire bricks on top of the stove. I create a bit more thermal mass on my wood stove, so that once the fire's gone out, it's still radiating a little bit of heat there, coming out slowly. So, do you think there's sort of some way with, the current underfloor heating? You say you can do it, it works best at a lower temperature, but you need bigger radiators. Do you think there's some combination with sort of, creating more thermal mass or charging up some more thermal mass even more during the periods of low energy prices? A bit in a way like the old storage heaters work, but taking that into account.
Sure. So in terms of the heat pumps, one of the, and I think that this will directly be connected to the question, one of the things that we've been chatting to some people in the industry about is buffer storage, so thermal storage to store the heat. The problem with thermal storage is that we need to be very careful in terms of how high we raise the flow temperatures. As we know, if we are storing heat in a thermal store, we need to increase the temperature of that water in that thermal store. So, but as we're increasing the temperature of the water in the thermal store, we're going to be reducing the efficiency of the heat pump. So, figuring out the optimal temperature to which we need to raise the thermal store is quite a difficult task, and that is something that we were working on recently. So, the past 3 weeks, we've been trying to work on how to optimize the heat pump and the connected to a thermal store that is then connected to the rest of the house. So we're storing some of that heat in the thermal store, and then we can still distribute it around the house.
That sounds like a very sensible way of doing it, but I guess that if you want to store the temperature, if you want to store that heat at a lower temperature, you're going to have a lot of thermal store rather than a smaller thermal store if you're trying to store it at a higher temperature.
Exactly, and this is where this is where that kind of trade-off between the flow temperatures and the prices and the efficiency of the heat pump need to be taken into account, and that is what we're doing. So, as you've seen from the presentation, one of the most important things and things that I think sets us apart is that consideration of the coefficient of performance at different flow temperatures and different outside temperatures. So let's assume that you have a buffer store, 1,000 liters, 1,500 liters, and you want to store heat in that store. As you said, you either need to raise that temperature quite high to store a lot of heat in there. But if you're doing that, for example, during the night when the electricity prices are low, it might be also slightly cooler outside. And if you're using an air source heat pump, that will impact the efficiency of the heat pump. So in that instance, we need to be, when we're trying to charge up the buffers, we need to be very careful into what is that optimal flow temperature that we should be picking for the heat pump to operate at, to raise the flow, the thermal store to, and what times we're doing it, depending on the outside temperature and also the electricity price.
Great, thanks. We've got another question in there. I don't know whether you can see that. I'll read it out anyway for everyone. What modifications are typically made to a house for the installation of a heat pump? I guess we're talking about retrofit now. So if you've got an existing gas boiler in there, what would you need to do if you want to convert it to a heat pump?
So very much depends on how the system has been installed before in that house. So a couple of things to consider. There might be instances where you might need to improve the insulation in the house, depending on how well insulated your house is and how old, basically how much heat you're leaking out. You might need to improve the efficiency. You might need to increase the size of the radiators. So when you're installing a heat pump, because we're trying to maximize the thermal area that we're using to transfer the heat into the house, we might want to have bigger radiators. This is where I mentioned underfloor heating is great because we have a huge area that is transferring that heat, which means that the heat pump can run at a very low flow temperature. With the radiators, we might need to just install slightly bigger radiators to make sure that we're still emitting we still have that thermal, the area that we can transfer the heat into the house. Apart from that, I think that those are the main ones that are usually considered. But again, if you're doing an installation, an installer would come in and kind of would be able to do the calculation, room by room calculation of the house, and see which radiators need to be replaced, which can stay, whether you need to improve the insulation of the house.
Great. Just following on quickly from that, some of it has been mentioned with regard to changes that need to be made. If someone's taken out a gas combi boiler, obviously there's not a hot water tank in there, so you know, and maybe there's some resistance for people, particularly on newer houses with lack of space, to put a hot water tank in there. What's your views on that?
That is one that I've forgot to mention. Yes, so heat pumps do tend to have a hot water tank that you would need to install by the side of the heat pump. In terms of the restrictions of space, there are some new technologies that are being investigated in terms of that you can use slightly. You can use the, which is on my tongue, forgot the name of it. We haven't had any installations with these, but it's a heat battery, I think, or
the phase change, gels and things.
Yes, so they allow you to store a lot more heat in a smaller space, which can help in those instances. But in terms of the efficiency of that and all those kind of questions, I wouldn't be able to answer because we haven't done any installations. All of our installations have been done with a heat pump that has a water tank next to it.
Right. Well, what I'll do now, if we've not got any more questions coming in from anyone new, then I will we'll leave it a couple of minutes and then I'll do the 3, 2, 1, and we'll leave it there. But certainly, as it stands at the moment, I'd like to thank you very much, Carolus. You know, I think you've been doing some really interesting stuff there. We have worked with you, and it's been a pleasure to work with you. Look forward to working with you in the future and sort of, you know, some of your new ideas. That'd be great. So anyone new want to ask a question? Well, nothing else has come in, so I will formally declare the proceedings over. I'd like to thank you all. If there's anyone that wants to jump into the breakout rooms, they're still there. But yes, thank you very much. Proceedings will close and we will go back to next Tuesday is the next session. So that's Tuesday the 9th. We'll have Matt Roderick from Energy Stroke Wonderwall, who's got a very more sort of practical solutions in the home to smart homes and smart energy. So thank you very much. From myself, Yanis. If you want to switch over to Yanis, Dave, so people can see Yanis, can wave at them, say goodbye. Yanis, wave goodbye, everyone. And to Carolus, if you can wave goodbye to everyone.
Thank you very much for having me.
It's
Nigel.
been a pleasure. And I'd just like to thank Dave, who's been behind the scenes pressing all the buttons, and it's been invaluable. We wouldn't have been able to do this without him. Thank you very much and goodbye from this session.